good afternoon in the island and good evening for everyone in Jakarta, in Indonesia. My name is Melinda. I'm a geologist working for Petronas Indonesia, but currently voluntary as a FOSI committee in Indonesia. So it is my pleasure to welcome you here today in a FOSI online talk series. I hope you enjoy your lunch and your dinner and ready to see the presentation. So amid this COVID-19 outbreak situation, hope everybody doing well, stay at home and keep physical distancing. I would like to extend my gratitude to our sponsors, Noble Energy Resources, for funding of this Zoom platform. With us together, already joined as some of the FOSI committee. Mas Ricky is our General Secretary of FOSI, and then Mas Erlangga is one of our committee as well. And Pak Win is already joining us as well as our committee for the FOSI, and the rest will joining us soon. We're glad to inform you that we established the FOSI YouTube channel. We uploaded all the video from the previous talk already. Don't forget to subscribe and like the channel, and please enjoy the video. And today's talk will be rescreening within the FOSI platform. Later on, we will get the permission from COM first, and then we will upload the video as well. I would like to thank you for joining us and get ready to be excited for a while because the topic to be discussed today is about technology application in the sedimentology and looking for hidden place in Indonesia. So this special presentation will tell you about the FTG technology and its role in the search for hidden place in Indonesia. And glad to inform you that the registered participants is about 100 and plus. It's quite huge because today is the weekdays. Still many people registered for our session tonight. And moving right along, it is now my pleasure to introduce our guest speaker. Really honored to have Dr. Colm Murphy, Chief Geoscientist from Bell Geospace. Many thanks for sparing your time this afternoon, Colm. I believe most of you know him very well, met him, or maybe already have his useful publications. And Com later on will rescreening the materials again, and we will share to us. And if anyone need the material, please wait until the end of the session. We will send a bit later. So before I hand over to Com, as usual, please allow me to give you some rules in order to make this meeting running smoothly. I would like to get your attention for a moment. The first one, I recommend to all participants to mute the audio and switch off your video during explanation from presenter to maintain a good connection. Second, the presentation may be recorded for a screening within the FOSI platforms. Q&A box can be found in the icon panels, usually at the bottom of your screen. Please enter your name for the committee to collect after the presentation. It will be answered live later on by Com. Later, you might turn on your audio and video to deliver your question. And hopefully Com is fine if anyone would like to ask him a question in the middle of your presentation. Just put your name in the chat box, and committee will notify Com later on to answer the question. So let's see how it goes. If many question arises, then we can have a break in the middle of the presentation. So well, ladies and gentlemen, please enjoy the talk and please welcome Com Murphy. Com, this is your turn.
Thank you, Melinda. Hello, everyone. First of all, I would like to say thank you to FOSI for the kind invitation to make this presentation here today and this evening to you all. We are certainly very appreciative of the kind invitation that there is. In the webinar, we're going to talk about the full tensor gravity gradiometry technology and its role in the search for hidden plays in Indonesia. This is quite an ambitious technique or a concept in many ways, bearing in mind the large and numerous basins that there are right across Indonesia. Many are producing, mostly in the western half, and many are non-producing or have yet to be drilled, and mostly in the eastern part. And we recognize over the last few years an increased amount of effort on behalf of the Indonesian authorities to encourage activity in these areas. There are many existing plays, many are well known, and many conform to the known and expected geological instances. The area is very rich in different opportunities in terms of geological models and geological plays across the area. We know that there are increased and encouraging aspects for going back into producing areas to find hidden plays and to find new plays, and perhaps even more hidden plays out in the east. And these will range from the standard, well-known concepts of the syn-rift, post-rift activities, to the intra and subvolcanics down in Java, to the deeper water plays in Kutai Basin, and also out in the Banda Arc region with the collisional tectonics and the many structures that they have generated. So in terms of the presentation, we're going to break it down into 3 simple parts and spend a little bit of time on each. The first one, we're going to talk about plays, and this is important because we need to put it into context in terms of what is a geological play and how it turns into an exploration play, and that helps us to frame the application for FTG. We'll also have a brief look at the FTG technology itself. What is it, and what do you get from it to help with making those geological interpretations? And then we'll spend the second half of the presentation looking at a range of case histories from across Indonesia. In terms of plays, a very simplified geological explanation, or in the geological play, is that it represents a group of oil and gas fields or prospects in a single petroleum system controlled by the same set of geological circumstances. And we quickly relate that to syn-rift activity or a thrust and fold belt activity or over a carbonate platform that may have developed. And then collectively, we would think about this as an exploration strategy or an exploration model to form our play model for the region or a region. And this is typically done to help to develop and exploit these prospects that occur in a singular petroleum system, whether be it in a basin, a region, or across a geological trend. And then as we look at it more as a visual of what that might mean, when it comes to doing your play modeling, you might start out working on it from a regional evaluation exercise and work through right into the prospect evaluation stage. You will see from the screen on the left-hand side that very much a part of the regional evaluation stage of a workflow is that where there's great consideration given to gravity and magnetic data, especially as they cover large tracts of land in a very quick, simple fashion, but they tend to be of low resolution, so realistically they help us to define where the basins, where the key structures, how is basement manifesting itself, and how it presents and identify these key basins. Regional seismic is often part of this, but it really comes into its own when it comes to basin evaluation and onwards. However, the step change from regional evaluation to basin evaluation can often be quite a protracted and prolonged period of time between initial data acquisition and evaluation to then deciding where do we need to put our seismic lines. And this is where the FTG has been most proactive in the last number of years, in fact, the last 20 years of operations worldwide from ourselves. We see it making that step change to expedite workflows and make them cost efficient into quickly identifying the key targets in the basin to plan the seismic. Of course, FTG, its strength is that it looks at density contrasts and it's very, very astute at imaging clear targets within a basin setting. Very often this adds value when it comes into a play evaluation and prospect evaluation stage, in the sense that there's an indirect step with FTG in that it can be used to help with the processing of seismic data to identify clear seismic imagery solutions, especially in areas where you have steep faults or you have volcanics or where you have salt or carbonate issues that might play havoc with your seismic record. So in having a quick overview in terms of what is it from the conventional gravity in the regional evaluation stage, this here is a subset from a satellite gravity data set over Sarawak. The anomaly pattern is quite fantastic and it offers good insight to understanding the regional geology. The pink colors are high density shallow basement rocks, the blue colors associated with sediment fill. The highlighted anomaly patterns are interpreted here as sourced by the same geological structure, basement, and with that it shows displacement by a regional transfer fault. And this is typically how one would use conventional gravity data, and it's excellent at helping with the regional scale structural mapping to helping to identify these basements and basement and delineate the key regional structures that influence the distribution of structures within that basin. But it is when we add the gravity field retrieved from the FTG and combine it with the satellite data that we truly get a full value of gravity for exploration and how we can expedite your workflow. Here, the FTG brings an immediate uplift in resolution. This value proposition from the FTG shows its remarkable ability to not only image the key targeted structure at depth, but also directly map complexity on the structures. And we see quite clearly where more detailed expression on those interpreted anomalies when compared to having just the satellite data. We have the long wavelengths and we have the short wavelength information from the FTG picking up on the detailed complexity on top of that basement structure. So every FTG combined with legacy data facilitates the direct mapping of the key geology on both the regional and localized and prospect level scale. The step up in resolution is now possible, establishes FTG as a key tool for efficient exploration. It produces a viable and ready to use high resolution gravity map detecting geology on both the localized and regional scale. And to help us to even go further to see what the value of the FTG is in this workflow, this is from the southwestern part, and we zoom in on it. The image on the left shows a series of parallel positive gravity anomalies. The white line locates the seismic image on the right. The positive anomalies correspond to fault blocks and the green-blue anomalies to basins. The seismic helps to confirm the FTG interpretation and that it firms up with identifying the basins and those shallow fault blocks. However, and perhaps more interestingly, the FTG actually adds value to the 2D seismic here as it predicts the lateral shape and form of the central fault block and helping us to identify where additional 2D seismic could be planned. So what is FTG? And this is where it's time to explain what the technology is and what you get from it. FTG is a full spectrum or broadband gravity technology that, when combined with legacy gravity data, allows optimal usage of gravity in an exploration context, from basin modeling to prospect and structural mapping workflows. The instrument itself directly measures the rate of change of the gravity field in all directions, and then through an intuitive processing workflow, produces a stable tensor and gravity field that is directly compliant with existing gravity data. A gravity potential is generated from each of the different outputs, there are 6 in total, and is then stacked and averaged to produce a stable high signal to noise product. In net effect, the FTG, it measures the rate of change of the field, as I was saying, in all directions of the field, and that's primarily sourced by the density contrasts in the subsurface. The net result will be a broadband data set and offers the highest resolution. Like all good science, the multi-measurements made by the FTG are described mathematically. Here we invoke matrix mathematics and describe the FTG output as a tensor. The tensor is described by having 3 component axes that vary in the vertical and both horizontal x and y directions. For geology, we relate how the field varies in each tensor component as a response to a target structure such as that depicted in the graphic, in this case a fault block. XX, YY and XY measure the rate of change of the field in the horizontal directions and the east-west and north-south directions, and particularly suited for mapping curvature as expressed on geological structures. These are often shown as rounded basins or structural ridges or thrust holes or elongated fault blocks. XZ and YZ measure the downward pull of the field as it changes in the X and Y directions, and when combined, directly map edges defining geological context, be it structural or stratigraphic, faults, unconformities, etc. Invoking matrix math rules, we can now investigate the meaning of what is actually presented. Laplace states that the diagonal sum of the elements ZZ, XX, and YY will always equal 0, and that there will be symmetry across this diagonal. This means that XY and YX are the same as it will be for the XZ, ZX, and YZ and ZY. FTG directly measures ZZ and the 5 independent components XX, XZ, XY, YY, and YZ. These individual tensor components are then combined into 3 primary elements that describe the rate of change of the field in the horizontal and vertical gradients, and the curvature of the field reflecting geological complexity in the subsurface. The first of these is TZZ, which is the vertical gradient and equates to the first vertical derivative normally computed from gravity. However, here it is the measured entity. It retains high frequency signal normally lost during processing of conventional gravity data. The impact value is high accurate depiction of the field as it relates to geology. We see clear tracking of low density sediment, sourced basin infill on either side of a higher density fault block, and is located on the flank of a shallowing basement structure going off to the south. The total horizontal curvature, or THC, is retrieved by combining the horizontal components. The maximum curvature shown in red, and the maps identify curved anomalous features associated with the basins and fault block geology. We see from the TZZ image that maximum curvature is directly associated with those basin responses. The final element is the total horizontal gradient generated by combining XZ and YZ, and the maximum peak values shown correlate with edges on ZZ, the horizontal curvature, and gravity anomalies, and are used to map contact lineaments. The rather large high amplitude anomalous feature here is picking up on the edge of the fault block and the low density sediment, which is quite good. Working with these tensor representations of the field often involved working with them individually to map contact lineaments, fold axes, and basins. However, it is also possible to work with a combined representation from these to build fast-track displays of subsurface geology. We do this by color blending the three primary tensor elements as a single map representation like that shown on the left. Color blending is an exciting development for geophysics as it enables a clear and concise means of visualizing multi-component datasets in a single display. Spectral decomposition in the seismic world combines different spectral content from 3D volumes using color blending to track geology. For FTG, we color blend the primary elements. We colorize the TZZ with shades of red, the total horizontal curvature with shades of green, and the total horizontal gradient with shades of blue. The mix of colors produced is reflective of the FTG response from the subsurface geology. Yellows and white colored anomalies indicate the presence of high-density fault block ridges, where you have a positive ZZ, a positive curvature, and a positive gradient. Whereas the green cayenne colored anomalies point to the presence of basins. We get the positive curvature in the gradient, but a negative ZZ anomaly. Anomalies colored blue are thin, locating contact lineaments, and the magenta colors point to high density change along fault zones, and that's coming from the positive ZZ and the positive gradient, indicating a step down faulted contact on the edge of a basin, on the edge of the basement, sorry. The impact of this is clear. We quickly map the primary structures in the survey area. The image on the left shows the gravity field retrieved from the tensor data. This is produced directly from the high signal to noise gravity potential generated from the tensor data. Its strength is that it has been generated from using all of the measured data and not just one single component. The final product captures the same signal bandwidth as that on offer with the tensor data, and is remarkable in its ability to retrieve coherent high-frequency signal with clarity. It behaves like the conventional gravity in the sense we get the long wavelength signal, but we also get the higher frequency short wavelength information as well, all in the one map. We can see this correlation more easily if we make the gravity anomaly field semi-transparent and expose the signal from the tensor data beneath. The sharpened expression on the basins and the fault blocks is quite clear. However, we also note that the detail from the tensor data that defines the longer wavelength anomalous gravity expression in the southeastern sector associated with the basement. Of course, there's more techniques that we can apply to working with the horizontal curvature and the horizontal gradient information. We rework those two particular entities to extract geological meaning information. And notice what's shown in here in the structure map, in that the warm colors are positive high density feature structures, and the green or colder colors are localized areas of sedimentary infill in this case. And then from the horizontal gradient, we pick up the faulted contacts that are evident on the edges of some of these blocks. When we combine a geological plane map, and to give a sense of what up here on the here we're picking up on the areas where there's greatest contrast and likelihood where there's a greater amount of low density fill on the flanks of the basin block itself. In addition, right up in the shallow basement, we see a hint of linear expression indicating that there's some subtle, perhaps new plays of interest on that block. and that's picked up where we pick up in individual sets of targets quite clearly with this automated procedure. This slide acts as a summary of sorts and what is provided as the FTG final product. The right-hand image captures the full tensor and its detailed expression of clear geological signal, and we know what we can learn from that for working the individual components. And that, whereas the image on the left shows the conventional gravity product from the tensor data. Its offering adds a sense of summarizing what it is we see for this example of the tensor data in terms of mapping shallow basement and then a series of basins on the northwestern edge. Retrieving a gravity field from the tensor is key to appreciation of what FTG adds to working with regional conventional gravity. Here we display the FTG gravity on the backdrop of satellite gravity data, and we call it a full spectrum gravity map. The correlation is remarkable as we observe coincident long wavelength information between the FTG and the satellite data, and then the finer detail from the FTG in defining clear geology with more confidence. The net effect is an uplift in gravity data quality, so having the full field available is advantageous for both explorers and basin modelers as it satisfies multi-purposes from detecting structures in early and late stage exploration to modeling for subsidence and rate of burial impact for basin assessment projects. And what do we, in terms of what does FTG offer you, the exploration community? It gives you a total gravity field or a full spectrum gravity by combining the FTG with legacy gravity data. It has the ability then to identify basement depth and density contrasts, and also to have a look at intra-basin complexity in terms of depth and density. And then quite clearly we are able to identify and map complex structures above basement in the form of fault blocks or closed structures or carbonate buildups and the like. And then it's directly suited for imaging as an edge mapping technology for mapping normal, reversed faults and strike slip faults across the basin itself. FTG is the current technology of choice by many operators for seismic planning. This can be 2D seismic infill, or programs are direct for 3D planning. It is a cost-efficient exploration technology. So that's the technical presentation on the FTG itself. We hope you found it useful, a good useful summary, and recognize that it's offering in not only being able to upgrade your gravity coverage, but help steer your exploration programs going forward by helping you with those play mapping exercises and in the search for finding new plays. We will now start to look at some more case histories and how this technology has been applied in Southeast Asia. Bell have acquired in excess of 500 surveys worldwide over the last 20 years and been in 47 countries, and I think we're soon gearing up to enter a new place of operations in West Africa for us, which will be our 48th country in the coming months. In Southeast Asia, we've been very proactive since 2012, embarking on quite a large number of survey programs. In this presentation, we're going to look at examples from over in the Banda Arc and a project we did with Saka Energy. We're going to look then into the Upper Kutai Basin in Kalimantan with work that we did with ConocoPhillips and Medco, and we'll also stay in the Kutai Basin in a project we did with Q Energy. These case histories have for the most part been published and presented at conferences held in various parts of the world over the recent years, and we thank our clients for their permission to be able to show these. We will also have some updated imagery associated with some of those projects to show in this part of the presentation. The first one we'd like to look at is a regional FTG survey. It was a 2-kilometer line space program acquired for Saka Energy over the West Yamdina area in the Tanimbar Islands on the Banda Arc. The Banda Arc locates the Miocene collision between the Australian plate to the south and Indonesia to the north, where both sides had endured a period of relative quiescence with sedimentation and a passive margin setting during the Mesozoic and Paleogene. The Australian side is well explored and shows immense prospectivity with a number of producing gas fields, most notably Abadai at 14.7 trillion cubic feet of gas. The objective of this FTG survey is to identify the prospectivity on the Indonesian side of the arc, and in particular, likely extension of graben systems to the north. The gravity signal retrieved from the FTG survey data indicates a northerly extension of the Calder graben across the Banda Arc. The positive gravity anomalies locate density contrasts within the thrust and fold belt, facilitating mapping of complexity within the arc itself. One of the first things that we do with the FTG data is to separate the signal somewhat and the frequency content in the final product. FTG is a good indicator of depth in the sense that there's a simple rule of thumb. Short wavelength anomalies are usually shallow sourced, and low amplitude long wavelength anomalies are sourced from depth. When we analyze this data set, we can break it into 3 depth intervals and produce an anomaly map for each interval itself. And so here we get to see a lot of the complexity in perhaps the shallow structuring in the survey area. We start looking a little bit more intermediate depth range, some 2 to 4, maybe 5,000 meters. And then we look at some of the larger regional scale effects from shallow to depths greater than 5 kilometers. In terms of mapping the fold belt, the primary objective was to delineate the structural control across the area and to identify the deeper basement beneath the thrust sequences associated with the Banda arc. The section as shown as an end interpretation is drawn from an integrated interpretation of the FTG, the magnetics and seismic information. The magnetic data that was acquired as part of the survey delineates zones of shallowing basement to the north, indicating a thick-skinned compression event, whereas to the south, the magnetics is rather quiet, indicating less basement involvement. And so we can identify where that separates from thick to thin-skinned activity. The high-frequency content from the FTG shows a reverse of anomaly character, that is, rather benign to the north and more energetic to the south. The linear anomalies delineate thrust fault activity and is interpreted as thin-skinned, that is having no or little basement interaction, is primarily sensitive to the shallowing thrust fault activity or presence in the shallow section. The intermediate frequencies from the gravity identify deeper basement, and where the survey extends to the north, perhaps a deeper basin away from the Banda arc. However, when you look at it closely with the section here, that perhaps what we see in the northern part is that less density contrast, and so we get a rather quiet expression. However, as we come to the southern part, we see 2 low density zones which correlate quite well with these deeper sequences. And by extension, we can interpret and infer their existence going to the northeast, allowing us to see some of the early Mesozoic, Triassic and Jurassic sequences beneath the thrust sequences themselves. The value, and then in the final image, is looking at the overall regional extent, pointing out the deeper basement blocks themselves. The value proposition from FTG for this project is clear ability to identify the primary structural trends and identify prospectivity beneath the shallow thrust faults. If we now move into Kalimantan and we'll have a look at the upper Kutai Basin area in the southwestern part. This is a project we acquired for ConocoPhillips back in 2016. The survey is designed with a 1 kilometer spacing, and the objective is to identify and map key structural trends ahead of the seismic planning exercise. You see the available seismic today was mostly to the east of the survey block itself. The area is quite extensive, that we know that there's the upper Kutai Basin off here to the northeast is likely to have continued going into the survey area, and that we have the Adang fault zone cutting through the northern part before we go down into the Burrito Basin down into the south. The FTG data were acquired over the entire block, and subset shown TZZ from the survey with forms of structures and synclinal structures, and also some of the manual lineaments. It is these traces of these lineaments, they are following compressional trends which are themselves reactivated fault structures that gave rise to the initial development of the upper Kutai Basin during the Eocene. The gravity signal retrieved from the FTG over the eastern part of the block delineates clear basin trends containing lower density rock yielding the negative anomaly pattern, or perhaps identifying localized pockets of low density fill in that part. Again, the value proposition from FTG here is a clear depiction of structural trends and basins, and that the data is proving instrumental for the seismic planning and the ongoing work being performed in the area. Coming into the upper Kutai Basin proper itself, it is an area that's well studied and well understood. We know that the Kutai Basin is most thickens greater going off to the southwest, and that's where there's in excess of 14,000 meters of sediment. In the upper parts, it isn't as well known. However, it is generally considered that 3,500 to 4,000 meters of sediment are present. The Eocene age drifting in the area is controlled by a series of northeast-southwest orientated basement faults, and these manifest themselves in a series of basins and blocks. And then after a period of quiescence, we had a carbonate platform developed during the Oligocene and the development of a number of possible build-up structures, with one hosting a known gas field. And then with a further subsidence and with the start of compression during the middle Miocene, we had some late-stage Miocene compression in this particular part, which yielded inversion along these pre-existing extensional structures, forming a set of antiformal ridges and being localized and helpful for perhaps entrapment of clastic plays. So in the FTG survey that was acquired here, the objectives are quite simple really, is to map basement, locate potential for carbonate presence, and map some of the clastic structure across the area itself. The data that has been acquired is shown in this slide. The image on the left is the TZZ, the vertical component from the FTG, and here we can see quite a series of neat, definitive forming anomalous patterns. Some are quite large and extensive, others are much more sharpened and localized. The total horizontal curvature, which is the combination of the horizontal components, helps to identify key structures in the survey area itself. And here, where we have the outline of a known gas field, we don't get such a strong signature pattern, but it is quite weak, indicating that the density contrast manifested here is quite low. And then we can look at the horizontal gradient. We're getting a high amplitude, large responses associated with the edges of a structure, to pick up unknown fault trends. Of course, we can now look at the gravity response as shown on the left, and this helps to formulate our appreciation for what the geology and how it's presenting itself to the gravity. It's dominated by these larger, longer wavelength signature patterns, forming a distinctive northeast-southwest trend, picking up on that Eocene basin trends in the area. But then we see a set of these shorter wavelength, narrower focused anomalies, which would indicate that they're, because of the short wavelength, they're more shallowly sourced. And we also see the subtle different expression associated with the structure hosting the gas field. When we strip away the tensor information, or strip away the gravity information, I do apologize, we make it semi-transparent, and we can see the impact of the tensor information coming through from underneath. And we identify a set of intricate and subtle fault patterns or lineation patterns within these basinal trends. And then having a look at the tensor itself, dominated by these very clear high density contrasts, very positive, but yet there are some emerging linear trends and density change elsewhere as shown. So we can see that there are perhaps two sets of anomalous sources in this area. There's those generating a longer wavelength and larger scaled anomalies, and those generating the shorter anomalies. And we can separate the signature content on the gravity map into a residual field, or what we call a depth interval anomaly, map 1, and a regional field, a depth interval anomaly, map 2. The DIA1 is generally sensitive to depths around 1,000 meters, and the depth interval 2 is from 2 to 5,000 meters below surface. And there's a clear distinction in difference in both. That the longer wavelengths are picking up on that Eocene basin trend quite readily, and yet we're seeing a lot of these lineations which could have been originally picking up on the edges of some of these structures, but in fact they're picking up, they're showing a sense of reactivation or higher density contrast in the shallower section. Of course, we can now work with the tensor information on each, and from each of these areas or these maps, and help to understand what the geological significance of these are. The image on the left is picking up on the fault to contacts from the analysis of the XZ and YZ in the total horizontal gradient, and we can see some higher strength and lower strength indicating a series of different trends. Looking at the DIA1 map and taking the structures from the total horizontal curvature, we get a clear set of sharpened responses, picking up on localized positive structures alongside some negative anomalous features, picking up maybe relocalized filled with low density sediment. And then in the longer wavelengths, we pick up the overall basinal trend itself and also some of the shallower sequences. Of course, what's interesting, we have now got a clearer expression of the structure hosting the gas field, and we can see potential for others elsewhere in the long wavelength image. One way then we can start analyzing these is to combine the lineaments with the structure maps for the two sets, and we can start facilitating and identifying a play concept for each. The first one on the left, we can identify a series of potential plays whereby we have shallow clastics caught up in these inversion-related antiformer closures. 6 are easily identified, and we get a very distinctive characteristic in each, and we can learn quite a bit from them. What's interesting about this one is that even though it's quite shallow, the likely source is emerging from the deeper part of the basin, and so it's probably charging and filling potential of interest in that area. And the same with these features up here to the north. And then on the map on the right, I previously alluded to these yellow colored anomalies, and we point them to the possible indication that there are perhaps other carbonate plays at depth in this area. So that's quite a neat way of working with the FTG. It shows a clear example of how quickly you can unravel the data and identify clear targets for immediate follow-up with other techniques. One of the last examples we have now from Kalimantan, it's actually over from the Samarinda anticlinorium area, which, as we know, that in the areas to the north is an immediate thickened basement feature emerging, and that the basin thickens greatly going off to the southwest. And in this area, we have a series of anticlinal structures having formed from compression and along what were previously known as extensional structures. And these are highlighted in a map here in the middle, that we got a number of anticlines and lineation trends showing anticlinal trend formations. These are quite prospective. The areas that are well known in the 6 structures identified, there is a combination estimated accumulation of over 2.5 billion barrels of oil and potentially 28 trillion cubic feet of gas. So this is a prime area and is in a very highly producing Kutai basin. Another feature of interest is one that we're going to be looking at in the next few slides, is actually the Pelarang anticlinal structure, which is, as you can see, parallels the Sanga structure. This is a structure. Pelarang is being explored and operated by a PSC by Q Energy. And in the workflow itself, you can see in the map on the left, it locates the area in Kalimantan. We have a look in the locating of the survey area in the license block, and we see that on the surface expression of Pelarang, it parallels a similar one from the known Sanga anticlinal structure. And then from this map I've taken from the paper by Kunjan et al. And published only recently, but it quickly points to the highly prolific gas and oil fields that are known. And then over Pelarang, we identify a number of smaller fields, a gas field, a Sambutan area, and also a number of additional leads that are known across the feature itself. The data that Q Energy have available to them is a vintage 2D seismic data set, some well information, and of course the FTG data set, which they've made very intelligent usage out of. The biggest challenge in many ways in Pelarang is improving the seismic imagery on the area. Seismic, as you know, tends to have limited value when it comes to resolving features that are steeply dipping, and this is no different in the sense that there's difficulty in unraveling and defining what is this anticlinal structure, how is it comprised, and what forms its complexity. When you look at the gravity map retrieved from the FTG, we can see quite clearly that we are indeed able to see very, very detailed, very focused expression on that structure itself. And then, of course, when we look around it, along that structure, we see there's some high amplitude and lower amplitude responses, indicating that there's variable depths to the tops of this feature in the subsurface, and pointing out that perhaps there's some localized complexity in the feature itself. And in the Sambutan area, this is presented previously by Q Energy at the IAGI show I believe in Sydney in the last few years, is that they identify potential for the localized development of a series of pull-apart basins, which emerge from identifying strike-slip fault patterns that serve to dissect and fragment this overall anticlinal structure itself. And this is very interesting, and so we have an added objective is to see what can we learn, can we use the FTG to help map some of these, more of these strike-slip faults that are impacting on the shape and form of that structure. So we start out our exercise by reviewing the data, and we have a look at the FTG, and we break it into three primary elements. We have the TZZ on the left. The area in here is actually an infill pattern. This was a survey acquired initially with a 400-meter line space survey, and then infill to 200 meters. So we got a sharper expression of some of the subtle changes along the feature in that area. We can have a look at the horizontal curvature, which remember is picking out the maximum it locates the primary structure in the area. And then we can look at the horizontal gradient and use this to identify the edges or where the maximum change is in the structure itself as it deepens with depth. We also have a look at the gravity map, which I've shown you previously, and we can see a clear, neat depiction. We can make this gravity go semi-transparent and start having a look at the contribution of the tensor information beneath, and we do quite clearly pull out the edges of the feature as it deepens with depth. And we also get the indication of presence of some more subtle complexity on the edges of the structure itself as well. And then the tensor helps us to formulate that impression quite neatly. We then build our structure and our lineament maps, and we combine them as such. We get a very expression of the lineations on the edges of the feature, and we can use that to help us to define in a modeling context of how the structure is behaving at depth itself. And then looking at the structures from the total horizontal curvature, we do get to see in here where the Samitan is that it's in a rather quiet area, and now we get these positive features on the edge, helping to identify where we have quite neatly the pull-apart basin, the localized basinal development in that area. And we combine them and we can learn more about the intricate plays that are in that data set. One thing that draws our mind, our eyes in many ways, is this blue anomaly that appears to be offset or displaced across a feature. So we can interrogate the impact of some of these. And the first one is the known in the Samitan area, and we can readily identify the imagery associated with the complexity and the structure. We also get a hint of it occurring at the southern end, where we get the development of more of these small pull-apart type basins potentially. And then when we look at the infill area, we get a lot more detail itself as well. In addition to that, we can look at the data and look for the color patterns and identify where they are offset and work it within the true geological reasoning context is to identify the potential for the strike slip faults and how they present it in the area across the block. Work done and in fact published recently also in a paper in 2020, and I don't have it here unfortunately, is that how Q-Energy have taken the FTG data and used it to help with the reprocessing of the vintage seismic in the northern area to get better definition of the basinal trends in this part of the anticlinal structure. Moving along, I just got one final case history to show you, and this is not from Indonesia, but it is from Malaysia. It is a work in progress, and it's something that's very fresh and recent on our minds, but it excites us and we wish to share it with you. It shows the advantage of how FTG can be used in conjunction with a 3D seismic work program. We're looking at a set of channel sands play. If you look at the image on the right, it's a seismic attribute map from this 3D seismic program, and we're looking at the bright amplitudes on the seismic record. Where we have the brightest colors in reds, there was a well drilled and are encountered hydrocarbons. When we look at the overall trend itself, it's following a north-northwest lineation pattern. If we now look at the curvature anomaly taken from the FTG, we see a similar north-northwest trending negative anomaly, indicating that that's where you have your channel fill, most channel fill itself. And that's quite an exciting opportunity because it allows us to look at and ask the question about the viability of perhaps other subtle low density features in the area. And the first step in that is to have a look at this map, but bring in the FTG curvature map underneath. And we can see clearly here the association. In particular, we know our feature here. In feature down in here, there's a series of bright amplitude coming through from the seismic, and that's sitting on this weaker localized structure that's probably on the edge of a channel. But in addition to that, you got all these other ones along in here, and they all seem to formulate and be present in those zones. So that's quite an interesting concept, in that the FTG can help to map the channel sands, and with the seismic it can help to shape and refine the interpretation and develop the play in terms of an evaluation exercise going forward. It is something that we're working towards and optimizing this particular application. So we're now at the end of the presentation, and I hope I've shared a sense of FTG's value proposition for exploration as we charted through the technical description and the varied case histories that I've shown. So in summary, we've worked through, in terms of plays, we talked about the importance of defining what are geological plays and how they're used to define the exploration strategy, and in particular how this helps to frame where FTG technology can be deployed in the work program itself. With the FTG, it is a multi-component technology at facilitating construction of a total gravity field. And from the FTG, we can directly extract information relating to structures and lineaments across the survey area and independently build a set of geological play maps that we can use to help steer an exploration work program. And then with the applications, we talked and described a case history from the Banda Arc area, looking in terms of a regional evaluation for FTG in a thrust and fold belt setting. We then looked at how FTG is used in the seismic planning exercise in the Upper Kutai, and moved on to discuss in more detail about its FTG's value for play mapping over carbonates and clastics in identifying those targets in the Upper Kutai Basin. And then in the last few case histories, we looked at the potential for prospect play evaluation exercises using FTG over Pelerang and also from Malaysia. So then we come back to this chart and we identify where now can we consider FTG's role in the exploration workflow and how it can be used in the search for hidden plays across Indonesia. We talked briefly, we certainly very much established the fact that FTG is very good in terms of going from regional to basin evaluation and right into the play evaluation. And then in the last few slides, we talked about its potential use for prospect evaluation. And we like to think that it is a good technology to have at all stages of the workflow, and it is a good technology. The data is always there once acquired, and it can be revisited at any stage in your work program to assess against what is an independent measurement of the density distribution in your survey area. So the value proposition from FTG, we believe that it's immense for exploration. Fundamentally, FTG offers clarity for assisting with de-risking projects, particularly for license evaluation. It adds value to seismic coverage, both with existing 2D data by facilitating mapping of structures from line to line, and with planning of new seismic acquisition, and all with a cost efficiency by working within budgets in optimal timeframes. These often lead to FTG being considered for well planning exercises where precise and accurate mapping of the 3D shape to prospects is routinely performed in a cost-effective manner. But in terms of adding value to seismic, FTG's role is primarily with play modeling and is both in terms of both defining and refining complex shape and depth targets that are often poorly resolved with seismic alone. Ultimately, FTG's primary role is as a seismic planning tool, from initial screening of the basin's prospectivity to detailed play modeling exercises ahead of a 3D seismic planning program. So to summarize and conclude, in this presentation I've described FTG technology and what it offers for the geological exploration community and how it has been deployed. I hope I've been able to successfully show you how it is a technology that can help with those play mapping and exploration on your projects across Indonesia, and that the value proposition from FTG is clear. It is a technology that brings a step up in resolution to your gravity data banks and brings clarity to exploration challenges faced in your work programs. Essentially, and in these trying times, we believe that FTG data is a key offering to advanced exploration. It works within budgets, facilitating work programs by bringing clarity to play model challenges, and it helps bridge that gap when existing data is often not the right quality or not in sufficient supply. Thank you. I'll be happy now to take any questions you may have, and I wish to thank you for your time. Melinda.
Okay, thank you, Com, for your very interesting presentations. This is very interesting technology, and I hope we can find a better play in the future, yeah, for this technology. Okay, do we have questions? We still have many slots for question. We still have many times. So please check your chat box at the center. And if you want to have a comment or discussion or question, please put your name in the list, yeah. Okay, the first one is from Pak Anung. Pak Anung, you can turn on your audio so you can directly ask to Com. Please turn on your audio, Pak Anung, please.
Hello, good evening, everyone. Good morning to you, Colm. Thank you for a very interesting presentation. I've been dealing a while with gravity data, but never been used FTG before. So there's a list of questions, and I try to make one or two. First is that one of the interesting part from your presentation is planning on the better support for seismic acquisition planning, right? And in some part of Indonesia, for instance, in Java, there's been a lot of curiosity to make exploration in the land area or onshore, where a seismic acquisition would be difficult. So it might be gives the benefit, but there is another challenge, is that in Java there is a shallower layer that has a problem, which is the volcanic layer that going to be impede the seismic signal going through. So is gravity would be and gravity, especially FTG, would be an answer to that, or how do you see that? The other question is that compared to the conventional gravity method, does it need a spatial tool? Does it need a longer time to make acquisition? And for acquisition processing, how long going to take for the project? Let's say for a 700 kilometers square of area, does it take 1 year, or does it take 1.5 years to finish all the project from acquisition to the deliverables of the product? Thank you.
Oh, okay, thank you. That's a nice question. In terms of the volcanics, well, first of all, volcanics, as they express themselves, tend to have a rather homogeneous density for the most part, be it lava flows or be it volcanic clastics. And these tend to be invisible when it comes to gravity surveying. Gravity and FTG in particular, it looks at lateral contrasts as opposed to vertical density contrasts. So if something is laterally varying and of homogeneous density, it will be blind to the FTG and gravity. And we've seen this around the world, looking at projects offshore Europe, where we map sub-basalt prospectivity, and also more recently in projects over the Deccan Plateau in Western India. Volcanics, so in terms of shallow layering of them, and FTG will see through them. But if it's still of concern to you, because you want to be able, you're finding it difficult to do the seismic, which is understandable. So you'd have magnetics to help you to locate where these volcanics are and map the top of the volcanic layer. And then you'll have the FTG and gravity to see the geology beneath the layer. And then in a quantitative modeling context, one will be able to predict where the base of the volcanics preside. Now, in terms of project workflows, FTG acquisition is quite fast. It's we acquired it on the aircraft as shown on the screen right now, and we can do upwards of near 1,000 line kilometers on a daily basis. So in an area where you have 700 square kilometers, we could probably turn that acquisition time frame around in a week or a few days to a week at most. And processing is very, very fast. Much of the processing is done whilst in acquisition mode. And then the last stage is done in the office, which would take no more than about 2 to 3 weeks. But on a project like 700 square kilometers, it would be much faster than that. And you'd end up with a series of results within weeks from the end of acquisition.
That's impressive. Okay. Yep. And what is the lateral sort of resolution of the data that you usually acquire? Is it?
Yeah, it's actually at the near surface, it's almost one-on-one. When we've done detailed survey programs, say in West Texas in the Permian Basin and elsewhere in the world, where we plan them at 100-meter line spacing to see the shallow section in quite detailed. But then as you go deeper, its resolution decays. It is a potential field measuring technology, and like gravity, it becomes less sensitive to detailed geology at depth. So in terms of, say, conventional gravity, its signal decays with the signal, with the distance squared from observation point to source. And FTG, it's with that distance, it's cubed, so it's much more sensitive to geology in the near section, but less sensitive at depth. Features at 2,000 to 3,000 meters depth, we're probably looking at features that are a minimum a kilometer in size and width and extent. But features in the shallow section, it can be 30 or 40 meters or less, depending on the density contrast.
Okay, thank you. That's very clear.
Thank you, Pak Anu, for the question. Next, we will have Pak Hendra Gandis.
Okay, good evening. I'd like to ask you about the fact that the data are already in gradient values. When you present something about curvature and other feature, do you calculate again about the gradient, or just you add up the data to obtain the other values regarding the gradient itself?
That's a good question. Yes, we do measure directly the gradient responses in the field, and these are just combined. It's a mathematical expression. There are numerous expressions out there that have been published, and that allow us just to, in a very simple linear fashion, actually, is just to combine the XY, the XX, and the YY component, and produce the curvature map. The biggest advantage is that we've measured it directly, and that we're not working with computed responses. You can do this with conventional gravity, but then to compute a gradient response from conventional gravity is highly dependent on the noise imprint within your data. So it's best to acquire it, to measure it in the first context, and with what we have, it's a 3D measuring technology. So we have 3 individual instruments making up the FTG itself, and the XY component is measured on each of them, so we get 3 measurements of it, so we get a very, very accurate measurement of that expression. And then the XX and the YY are combined with that precise measurement of XY to give us a direct curvature map from the data.
Okay. My second question is about how to obtain the data at the specified depth. Did you use the gravity value or also the gradient value?
We would work with the gravity. We would take the gradient information, and in our processing stream, there are 6 outputs, and we estimate a gravity potential from each, and then we stack them with, and so we end up with a conventional gravity response. That is the one that we would use to predict depth, or to, because it's best working with the conventional field rather than it is with the gradient of the conventional field, because you can get quite a false response. So that we would use the gravity retrieved from the FTG to help us with depth estimation in that regard.
It's a proprietary algorithm or useful algorithm?
Yeah, it is proprietary, I'm afraid. In fact, there is published information. Well, it's partially published. It was presented at the IAGI show 4 years ago by one of my colleagues, and it was in the Airborne Gravity Workshop, and he gave a fantastic presentation. And a video of the presentation is available on the IAGI on the Geoscience Australian website, but the written document has yet to appear in print form. And but it's a well-established technique at this stage, and I believe I might be able to share that document with you, because there is a pre-proof copy available.
Okay. Thank you very much.
Thank you.
Good luck.
Thank you.
Thank you, Pak Hendra. Next, we will have Pak Win. Yeah, we still have many slots for the question. Pak Win, you can turn on your audio, please.
Thank you very much for a very insightful and very thorough presentation. As always, I I'm the first to admit I don't fully understand gravity and all of its relatives, and I'm always willing to learn. Fantastic technology advances from the last time I really saw these. I'm going to ask you basically two questions out of ignorance. The one is a virtually new play in Indonesia, and it's kind of being canvassed because it's being used in old areas because people didn't go deep enough before. I'm referring to fractured basement reservoirs. Is there any combination of the products that you would put out that could start to show something as I'm afraid it's going to be too subtle as far as the density contrast between rock solid basement and that which is either weathered or laterally changing for fractures?
Good question, and I'll be perfectly straight up here and say it is possible, but only if that shallow fractured basement prospect is indeed shallow. And if that were the case, then we would plan a survey with an appropriate line spacing to determine how viable it might be. You've seen in a response example there from when I was describing the technology, I talked about a shallow basement event and how we had a series of basins developed going off the northwestern slope from that. But up on the shallower basement, we could see a series of incised low density patterns, and we would interpret them as being perhaps something that might be of interest as a possible fractured basement play in the shallow section. Now, that's rare it'll work in that shallow section. If you push that down 2, 3, maybe 4,000 meters, I'm afraid FTG wouldn't be of much help in that regard, simply because these features might be very small. Well, if they were to be detected, they want to be quite large, a kilometer or 2 kilometers wide, rather than say 100 meters or so wide.
Well, that's fine. Good perspective. You know, with this whole sort of new prospect, this new play, there's no answer. So what I've seen is the combination of different technologies or techniques to de-risk. You're not going to get a full answer, but if you get enough applications or technologies applied, you would focus. You would maybe high grade your portfolio.
Very true, and in fact, so many of these techniques can be used to eliminate possibilities as opposed to find the answer itself, or that you can use, say, gravity or a magnetic technique to assist with the seismic imaging of another aspect of the program that would, once removed, then in the residual products you might learn more information about what you're seeking. Yeah, it's all about de-risking, you're quite right, and to select the technology, the appropriate technologies at the right time to do that.
Let me, if I may, let me take you far afield of your excellent presentation. I have a very good friend who's in geothermal exploration, and we are always comparing notes to see how our disciplines are the same or how we're vastly different. You have any insights for FTG into a geothermal exploration?
I guess there is an application. I mean, geothermal is it's a learning exercise in many ways. I mean, we initially did work back in the mid 2000s, a project in New Zealand, and I was looking actually at epithermal gold deposits in the Taupo volcanic zone. But part of that was a geothermal application, in the sense that they were looking at these hot springs, and it was all shallow, and we were able to map the structures quite neatly. And then the other side of it is looking at the deep hot rocks at 4, 5, 6,000 meters. That's probably more conventional gravity in terms of identifying the density of the feature that you're wanting to looking for. But then there is the in between, the kind of the hydrothermal, the low enthalpy hydrothermal heating possibilities, whereby you might look at, say, structures. There could be a carbonate platform, or there could be something sitting on top of a basement feature that's crystalline basement, metamorphosed, or something that's hot rock. And this particular carbonate block may have pore space, a potential reservoir for water that could be heated directly from the source underneath. Now, FTG can have a role in that in terms of identifying where that structure is that resides on top of basement, and help to pin down the possibilities. So it's something that we would look at. We would never say no, but normally when we set about to investigate applications coming in from interested parties, is that we request a geological cross-section, and we'll conduct some feasibility modeling studies to see if there would be a signature, and if there is, fantastic, and then we can use that to set about and design a survey program to map the feature more evenly. Yeah. So yeah, geothermal is there. If there is an application, I know it's not quite pinned down. I guess hasn't been enough activity in that area for us yet, but it's certainly something that would be of interest.
Excellent. I'll be sure to have my buddy come take a look at your presentation on the YouTube stations here soon, okay. The channel, and he'll be quite pleased that I brought up geothermal. Okay. Let me something else occurred to me, and like any good modeling sort of technology, you get the nice picture of the plane here. So depending upon the survey, is it all airplane towed, or is it helicopter towed, or what?
These days it's all on the Basler BT-67 aircraft as you see it. The instrument itself is quite large. I mean, when we first started doing survey work, it was on a boat on the open seas, on large seagoing vessels. And then in the early 2000s, we tested the instrument on a small aircraft. We put it on a Zeppelin airship for kimberlite hunting in Botswana. But then we settled on the Basler, as you see it on the screen. And we haven't put it on a helicopter. I think to fit the instrument on a helicopter, it want to be significantly reduced in size to fit on a manageable helicopter. Otherwise, the helicopter could be quite as large as some of the smaller aircraft and become very expensive to operate. The Basler aircraft is an old DC-3, and it's been modernized and upgraded. It's got modern avionics and engines and the like, and it really is a powerful workhorse. We have instruments permanently installed, and we are up and running within days upon arrival on the survey area. We can mobilize worldwide quite efficiently, and we own 3 of them. And it's been it's probably considered the best platform to use for gravity gradiometry, as the data that comes off it is very consistent. The noise, or the signal, the non-geological signal, as you might call it, if you're an engineer, it tends to be quite consistent and quite easily removed. And it's considered probably the best platform for airborne gradiometry in the business.
Great fun. Stimulates the imagination. Thank you very much. Appreciate it.
You're welcome.
Okay, thank you, Pak Win. Next, we will have Pak Zain, yeah?
Yeah, hello?
Hello.
Yeah, thanks for your very nice presentation. But I saw in your slide that the way we interpret the result is like more in the amplitude of gravity itself. But do you think it's worth to do inversion in either it's 2D or 3D? Because we know that we have more measurement in here, like the gradient. So probably the modeling result will be more constrained by more measurement in here. Do you think it's worth?
Absolutely, yes, and it is being used. There are many consultant and work groups out there around the world who do a lot of good, solid inversion work, modeling work with FTG, some simultaneously, others in the joint effort with other technologies, and give fantastic results. The FTG, we have our own kind of a robust inversion method. We call it migration, and whereby we migrate the signal into a depth density model or field, and we use that to help us to discriminate depth sensitivity and predict density for the individual entities that are predicted. It's fast, it's robust, and it's done initially in an unconstrained environment to quickly identify what's interesting, and then you can go through the full parameterized inversion exercise, which can be quite exhausting and quite protracted, and they're often best done when you've actually got good constraint. Now we have that expertise as well, and we feed in depth density relationships from well information. We got seismic constraint, and we can use that to predict we predict a series of results from the inversion of the FTG, and then analyze them statistically, and you can fine tune as to what's the most likely scenario. So yes, it is possible, and it is something that is done. I think what I want to do in today's presentation was to show the power of working with the data in a very, very fast and efficient way, especially to identifying structures and lineaments, and how they can be used to build a plane map very quickly, and that you can use to feed that into your own workflow, whether it's the geological reasoning stage as part of a team, or you might put it in through a machine learning exercise. You'll have the information to do that at hand. And then go from there into and then use that to steer your inversion studies. So yeah, it is possible, and there are many good technology out there that can do it. Yes.
Yeah. So the second question is about: is there any effect of speed or of your air flight or speed of your plane? Let's say if you go slow, or you going slow, or you're going too fast. Let's say if you want to high resolution, you're going too slow. Or if you want to very broad or low resolution, you're going fast. Is there any effect of speed or velocity of your flight?
Yeah, speed does impact it, and we always actually fly our surveys at the same speed when in survey mode, and that's around 100 knots. Works out to a sampling rate of about 60 meters, reading every 60 meters, about 60 meters per second, and we do that constantly. The impact for, say, resolution, high resolution, you would fly with lines spaced, say, 100, 200 meters, 400 meters apart. If you want low resolution regional studies, you might do 2,000 meter spaced lines. That's the difference. So, but it's always acquired at the same survey speed, but we designed the survey then to be either, we go to same slow speed to have high sampling rates along line, or then we, depending on the nature of the project, whether it's to be looking deep and over large areas, we can go wide line spacing, and then we can infill to tighter line spacings over particular parts of that survey block to get more detail. So that's how we do
it. Okay. Thank you.
Okay, thank you, Pak Zain. The next one we'll have Pak Erlangga.
Okay, thank you for the short but comprehensive presentation, Cole.
You're welcome. Thank you.
Question is simple and probably stupid. So, considering to the fairly good resolution, and in some example, I saw that it could detect a gas field, like if I'm not wrong, in Kalimantan examples. I'm just wondering if it could go just an extra miles, such as possibility to use this FTG for like a fluid movement monitoring, especially in gas over a time, maybe in the future, or such as like a 4D reservoir monitoring. Maybe not right now, but probably in the future.
Yeah, good question, and I'll give you a simple answer in many ways, because that was something that we were asked about a long time ago when we were doing the marine survey work, and studies were done on that to show, yes, it is possible to use FTG for reservoir monitoring, but it was restricted mostly to fields in the shallow, say 1,000, 1,500 meters depth maximum, to get the optimal value of the FTG. Now, there's another side too, of course. Conventional gravity is very good for monitoring. Conventional gravity with meters installed, permanently installed, say, along the surface. And this was done in Alaska. And they make the gravity measurement every year, I guess, or they record it. And they're able to, looking at the differences between the measurements each year, they're able to track the change in fluid movement from the introduction of water and the extraction of the hydrocarbon. So conventional gravity is probably very much the favorite tool in that, because it looks at the long wavelength variations as in a field. The FTG can be very good if it's shallow. Maybe the conventional gravity might be better in something that's deeper, of which many of the fields tend to be. There is an application, but it's something that has yet to be pursued truly, I guess.
Okay, thank you.
Okay, thank you, Pak Erlangga. Is there any questions before we close this session? Any question? Okay. Okay, I think that will be the last question, Colm.
Okay.
And that will end our discussions. Thank you very much for the interesting discussion, very interesting presentations, very interesting technology. And FOSI very honored to have you. And we're looking forward for the next session if you have anything to share in FOSI. Yeah.
Okay.
And I hope you stay safe and good luck for this technology. And that's for me and Melinda for the closing. Yeah.
Thank you very much for your time, and it's been a pleasure to have been able to do this presentation. And yes, stay safe, everyone.
Thank you, Cole.
Melinda?
Thank you very much, Colm. So please let us know whenever you are visit Jakarta later on, and meet you in person in the future later on. All right. Thank you very much, everyone, and have a great day. And thank you very much, Colm, for spending your time. So later on in the video, we will get the permission first before we upload to the YouTube.